Welcome back. Today we are diving into computational physics with a focus on simulation, specifically exploring dynamic display, kinematics, and animation. We will look at how we build a simulation from scratch, choose proper physical scales, and utilize tools like IPython's display module and Matplotlib's animation module to bring our physics to life. By the end of this session, you should be comfortable breaking down a simulation into its core components, like state variables and update rules. You will also learn how to choose appropriate display scales and implement frame-by-frame as well as tool-based animations for particles, pendulums, projectiles, and traveling waves. Let us begin by importing our essential libraries, NumPy, Matplotlib, and the animation and display packages. In this continuation of our setup code, we configure our default plot dimensions and turn on the grid lines for clearer data tracking. Notice the two Boolean flags at the bottom, which control whether we run live display loops and render animations during a session. We keep these adjustable so that automatic notebook executions remain fast when needed. This confirmation stream shows that our libraries have loaded correctly and reminds us of our default rendering configuration. Having a simple confirmation print statement is a great habit in computational workflows to ensure that your environment initialized without errors before starting heavy computations. Let us look at the foundational anatomy of a simulation, which is essentially a controlled numerical experiment. Every standard motion simulation requires tracking state variables, setting fixed physical parameters, defining initial conditions, choosing an appropriate time step, establishing a mathematical update rule, and setting up visualization boundaries. A simulation is only as good as its display limits. If your plotting box is poorly sized, even perfectly correct equations will look entirely wrong. Our first source-preserved example focuses on a simple one-dimensional particle moving at a constant velocity. Here, our update rule is straightforward and analytical, given by position as a function of time. Before we write any code, we establish a natural timescale by dividing our total simulation box length by the maximum expected speed, giving us a reliable time of flight for our visual boundaries. Moving into the code implementation for our single particle, we initialize a random number generator with a fixed seed to ensure reproducibility. We then define our physical bounds with a box length of 10 meters and a maximum velocity of 2 meters per second. Using these boundaries, we establish our time array across 60 frames and sample a random initial position and velocity. This next segment of the code handles printing our randomized physical variables and setting up our diagnostic plot. We use standard Matplotlib plotting commands to map position against time, and we add a dashed horizontal line representing our right physical boundary so we can visually verify if our particle remains inside the simulation box. The printed output stream confirms our generated parameters, showing an initial position of roughly 1.31 meters and a steady velocity of 0.92 meters per second. Given our maximum velocity constraint, our chosen timescale spans exactly 5 seconds, leading to a final position well within our 10-meter boundary. This static diagnostic plot verifies our calculations before we attempt any animation. The solid blue line displays a perfectly linear increase in position over time, which matches our constant velocity kinematic formula. The dashed line at the top clearly shows where our right boundary sits, confirming our particle has plenty of room to move. Now let us explore how to create a live animation using a frame-by-frame display technique with IPython's display modules. We write a custom function that takes a particle's position and clears out the previous frame using clear_output before drawing the new frame. This teaches us the fundamental mechanic that an animation is ultimately just a timed sequence of individual static frames. This section of the code contains the conditional loop that handles the real-time playback. If our live display flag is enabled, the notebook loops through our position array, constantly clearing the cell output, displaying the updated figure object, and pausing for a fraction of a second to control the perceived animation speed. If the flag is off, it simply renders the initial state as a placeholder. This final piece of our frame-by-frame configuration renders our placeholder plot and prints a helpful reminder stream. This stream explicitly tells the user that the live display loop was skipped by default, instructing them exactly which Boolean variable to toggle if they want to view the live execution. Here is what an individual frame looks like during the execution of that live loop. At frame 11, we can see our particle rendered cleanly as a single blue dot, moving along our one-dimensional black coordinate axis line. The axis limits remain locked between 0 and 10 meters, providing a stable visual framework for the motion. We can naturally extend this concept from a single particle to an arbitrary number of particles by transitioning our scalar variables into multi-dimensional arrays. In this code block, we initialize 8 distinct particles, giving each a unique initial position and a unique velocity. By leveraging NumPy's broadcasting features with none indexing, we compute all trajectories simultaneously without writing slow Python loops. This continuation block completes our multi-particle setup by looping through our newly constructed position arrays to plot each individual trajectory line. We label each curve numerically and add a multi-column legend to keep our final graph organized and readable. The resulting multi-particle plot displays 8 distinct linear trajectories, each starting at a different initial position and climbing at a slope proportional to its randomly assigned velocity. This array-based approach allows us to scale up our simulations efficiently, handling large collections of matter without changing our underlying core logic. Our second example introduces a simple pendulum operating under a small angle approximation. Mathematically, the angular displacement is modeled as a cosine wave governed by an angular frequency dependent on gravity and length. This example is highly valuable because it demonstrates that our simulated state variable, which is an angle, must be converted into Cartesian coordinates before we can plot or animate it in physical space. In the code implementation for our pendulum, we set standard gravitational acceleration and a string length of 1 meter. Then define a small initial angle of 5 degrees converted into radians. We calculate our angular frequency and period, construct our time array to span exactly 2 full oscillations, and compute our angular states over time. Here, we transform our calculated angles into Cartesian coordinates, using standard trigonometric relations to track the actual coordinates of the bob. The code then prepares 2 distinct visualizations: a standard time series plot of our angular displacement, and a geometric coordinate plot outlining the circular path that the pendulum bob traces out in space. This short continuation block finalizes our geometric coordinate plot by calling the show function. It ensures that all previously configured layout adjustments, aspect ratios, and axis limits are fully compiled and rendered cleanly on the screen. Our printed output confirms our theoretical values, displaying an angular frequency of roughly 3.13 radians per second and a period of just over 2 seconds. It also re-verifies that our initial angle was correctly interpreted as 5 degrees, ensuring our small angle assumption remains physically sound. Our first pendulum plot shows the time history of the angular motion. We observe a flawless, undamped, sinusoidal oscillation that peaks exactly at our initial value of 5 degrees and completes 2 full cycles across our 4-second time window, validating our analytical solution. The second pendulum plot shifts our perspective to the actual spatial coordinates of the system. The blue line and marker represent the physical pendulum string and bob anchored at the origin, while the faint orange arc highlights the path of the bob. Locking the aspect ratio to equal ensures that this arc represents a true physical circle segment. Our third source-preserved example focuses on 2-dimensional projectile motion derived from classic kinematic equations. Because we are using pre-established analytical formulas for horizontal and vertical positions, our simulation serves primarily as an interactive tool for visualization and scale verification, rather than a step-by-step force integrator. We initialize our starting coordinates at the origin and set a launch velocity at a 45-degree angle. Next, we calculate key physical scale estimates, including the time to maximum height, total flight time, horizontal range, and peak vertical clearance. These mathematical scales are immediately used to construct an appropriate time vector and compute our coordinate trajectories. We then set up a plot to map out the complete trajectory path of our projectile. This code block finalizes our projectile plot settings. We add a black horizontal line at 0 to represent the ground boundary, apply clear axis labels, and implement an equal aspect ratio command. Ensuring equal axis scaling is critical here, so that the parabolic trajectory maintains its true geometric shape without artificial vertical stretching. The resulting data stream provides our calculated flight metrics, showing a total airtime of roughly 3.17 seconds, a maximum height of 12.33 meters, and a total horizontal range of nearly 50 meters. These values give us the exact spatial boundaries required to frame our plotting window accurately. Our static trajectory plot confirms a beautifully symmetric parabola that begins at the origin, reaches its peak height exactly halfway through the journey, and returns to the ground level just short of the 50-meter mark. This perfect visual agreement gives us full confidence to move forward with animation. We now move to a more robust, professional animation methodology using Matplotlib's Func Animation. This powerful tool relies on a structured framework consisting of a target figure, an artist object like a line or point, an initialization function, and an update function that modifies the artist's data frame by frame. Let us see how this handles our original one-dimensional constant velocity particle problem. In the initialization script for Func Animation, we configure our empty axes, establish our labels, and generate an empty plotting object designated as our particle point. We also clip our position array to ensure the data stays safely inside our visual boundaries. And we define an initialization function that clears out the artist's data before playback begins. This segment defines our core animation update function, which takes the current frame index and updates our particle point's horizontal position while holding its vertical coordinate at 0. We then instantiate the Func Animation object, passing in our update function, our frame count, an explicit playback interval in milliseconds, and enabling blitting for optimized rendering performance. This code block handles the final notebook rendering logic. If our animation rendering flag is active, it converts our compiled animation object into a JavaScript-based HTML widget for interactive playback. Otherwise, it prints a message confirming the object was built successfully and instructs us how to display it. The output shows our compiled interactive HTML object placeholder. When executed live with rendering enabled, this object injects a fully functional media player directly into the Jupyter Notebook, complete with play, pause, and frame-by-frame scrubbing controls. Our final example investigates a one-dimensional traveling sinusoidal wave. The wave is mathematically defined by its amplitude, wave number, angular frequency, and phase constant. A crucial physical takeaway here is that altering the mathematical sign separating our spatial and temporal terms directly dictates whether our wave propagates to the right or to the left along our axis. To build our wave, we define an amplitude of 1, a wavelength of 2 meters, and a wave speed of 1.5 meters per second, from which we derive our angular frequency. We write a flexible wave function that accepts a directional parameter to easily toggle propagation behavior, and we set up our spatial and temporal coordinate grids. This section of the code handles two tasks. First, it loops through specific time snapshots to generate a static multi-phase overlay plot. Second, it initializes a brand new subplots figure and an empty line artist that will serve as the target foundation for our upcoming wave animation loop. Here we define the structural functions required by Func Animation. The initialization function clears our waveline artist, while our update function evaluates our wave equation across the entire spatial array for the current timeframe. We then feed these functions into the main FuncAnimation constructor, setting a smooth playback interval of 50 milliseconds. We conclude the wave simulation script by closing our working figure to avoid duplicate rendering artifacts and computing our theoretical wave speed. The conditional block once again determines whether to output the fully animated HTML widget or to display our successful creation text streams. Our static snapshot plot displays 4 distinct wave states captured at half-second intervals. By tracing the peaks of successive colored curves, you can clearly see the wave crests shifting systematically to the right over time, confirming that our programmatic sign conventions match physical reality. The printed output stream confirms our wave speed calculation, returning a value of 1.5 meters per second. This matches our initial input parameter perfectly, providing a solid mathematical verification of our wave grid relationships. The notebook returns our final interactive HTML object for the traveling wave. This represents the pinnacle of our lecture's tools, allowing students to observe a continuous, fluid physical wave propagating seamlessly across space right inside their browser. Let us review some common pitfalls in introductory simulations. Avoid picking arbitrary timescales without calculating physical bounds. Never guess plot limits blindly. Do not confuse your mathematical state variables with your plotted display variables. And never attempt an animation without checking a static plot first. Always calculate your trajectory arrays completely, validate them visually, and only then proceed to animate. To solidify these concepts, here is your guided practice. Try adjusting the maximum velocity to see its impact on flight time. Increase your particle counts to practice array broadcasting. Expand your initial pendulum angles to observe where the small angle approximation breaks down. And experiment with different launch angles and wave propagation signs to see their direct physical impacts. In summary, we have learned that a robust simulation bridges physical models with rigorous numerical scaling and clean display workflows using IPython and Matplotlib. Now that we have mastered these kinematic simulations using analytical equations, we are ready for part 2, where we will build dynamic, force-based simulations from scratch using Newton's laws and the velocity-Verlet integration algorithm. See you there!